So here's our thought puzzle. It says this. Nellie is suspended by a rope inside an elevator, like in the little picture. Two forces act on her. The rope force, tension, T, and the force of gravity, what yesterday I nicknamed the obvious one, mg. By the way, what's another word for gravity? It starts with letter W. No, now. Weight, yes. Weight is newtons, mass is kilograms. Don't mix them up. When the elevator accelerates upwards, A, tension is bigger than mg. B, tension is the same size as mg. C, tension is smaller than mg. Or D, I don't have enough information. That's part one. Part two, suppose somehow the outer cable that supports the elevator snaps. The net force on Nellie would be A, 0, B, mg, or C, I need more information, like her mass. So let's look at the first puzzle. Once again, we're going to vote. Once again, how you hold your hand up is how sure you are of the answer. In this situation, when the elevator accelerates upwards, which of those four statements is correct? Who says, Mr. Dewick, A is correct. Tension is bigger than mg. A. I got 1. I got 2. I got 3. No, I got 2. Withdrew? Objection withdrawn? Okay. 2. Who says tension is equal to mg? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Who said, no, tension is smaller than mg. We need more information. Okay. What was the theme of yesterday and today's lesson? It was 3 words that I also gave you an acronym for, FBD. This is a job for a free body diagram, because a good free body diagram will make this clear. Fahim, I'm going to represent Nellie with a dot. What are the forces acting on her? Get the obvious one. Which way? I'm looking for a word that starts with letter D. Thank you. What else? Well, tension, the question says, the rope. Tension bigger, smaller, or the same size as mg? And how do I know? I'm going to use Newton's laws. Which way is Nellie accelerating? How do you know? Which way is the elevator accelerating? I'm going to ask you a series of questions. Although all the questions are going to be different, I want the same answer, and the answer is going to be up. Which way is the elevator accelerating? Which way is Nellie accelerating? Which way must there be a bigger unbalanced force? Which force is that? What's the correct answer? A, B, C, or D? Has to be. Tension has to be bigger because we're accelerating up. That's the power of Newton's first and a quick free body diagram. And as you do more and more free body diagrams, that'll take you 2 seconds, maybe. Absolutely. What if she was accelerating down? Well, then tension would be smaller, gravity would be bigger. What if she was moving at a constant speed or at rest? In both of those situations, constant speed or at rest, what's the acceleration exactly as a number? I heard someone start to whisper it. Loud and proud. So if the acceleration is 0, that means the forces must be, I'm looking for a word that starts with letter B. That would mean gravity equals tension. I can tell you because of Newton's first, that has to be. All right. Suppose somehow the outer cable that supports the elevator snaps. The net force on Nellie would be, well, if the cable snapped, would she accelerate? So if this cable suddenly snapped, and let's assume there's no safety devices on the elevator, so now it's just going to drop. Will she accelerate? Will the elevator accelerate? Is she in the elevator? Will she accelerate? Yes, which means that can't be right, because if she's accelerating, the net force cannot be 0. That's Newton's first. In fact, if the cable snaps, that's the free body diagram. What is the net force acting on her? Well, there's only one force. Jonah, which one? Now let's continue from where we left off last day. I'm going to do a little bit of a quick review for the benefit of people that were away, but also just to jog your memory. So we actually didn't start the lesson until the second page. We just did an example of F equals ma and what you could do with it. But we said a free body diagram, we represent the mass with a dot. And then we put arrows showing the forces acting on that mass, roughly to scale. What did I mean by roughly to scale? Aiden, if you know two forces are the same size in magnitude, make the arrows the same size. If you know one force is bigger than another force, make that arrow obviously longer than the other force. Okay? We could figure out which forces were missing by using Newton's laws. And then here was the big punchline. The equation that we are going to use, and the only one you'll get from me if you take Physics 12 with me next year, is this. Winner minus loser equals F net. Oh, but then we said F net was MA. So we said winner minus loser equals MA. Who's the winner? Whichever way we're accelerating. Who's the loser? The opposite direction that we're accelerating. This is also going to take care of any negatives or positives. In this unit, we are no longer always going to say down is negative and up is positive like we did in kinematics. We're going to say positive is what makes the math easier. That's actually a better place to get to anyways. Not be rigid. Let's do what makes the math easier. And we got to, I think, example 7, and I have a little note here reminding me to record the lesson, which I have, and hit pause. Example 7. I like example 7. I like example 7. Example 7 is a nice question. It is. Okay, so what does example 7 want me to find? You're feeling a little tension right now, different kind. Okay? This is a job for a free body diagram. Now, how do I know? What does it want me to find? That's one force. Is there another force in this question? The obvious one. What? Acceleration's not a force. Gravity. Is there more than one force? Probably until you get really good, you're going to want to do a free body diagram. So I'm going to represent the mass with a dot right there. Acacia, what are the forces acting on this? Get the obvious one. Which way? Yep. And you'll notice I just started putting the equation for gravity. The symbol for gravity is Fg, but since Fg equals mg, I often just put the equation there. Okay. What else? Tension. Bigger, smaller, or the same size as gravity, and how do I know? Which way are we accelerating? So who's winning? So tension is going to be, yes! Good. And I'll really exaggerate it so it stands out. So it's obvious. Okay? I mean, tension might only be a little bit smaller. I don't know, but I'll make sure I notice. So now I can get my equation. Who's winning? Mg minus, who's losing? What's that going to equal? Always. This is why I said to you, the only equation you're going to get from me is F net equals MA. Well, winner minus loser equals MA. We'll derive the rest of it because I cannot come up with every single equation. Kinematics, there was 4 and that solved everything. Here, no. If I was trying to find the acceleration, how would I get the A by itself? Scott's theorem. Cole, what was Scott's theorem? How would you get the A by itself? So as far as I'm concerned, it's fair game for me to give you the same situation, tell you what the tension is, and say, find A. Okay. But they want me to find tension. What's right in front of the T that I don't like? A symbol sitting right there. The minus. I'm going to show you a wonderful, clever trick in formula manipulation. I could divide by -1 to get rid of that negative. Instead, I'm going to plus the tension to that side. Now it's positive. At the same time, look up, look up, look up, look up. Keep looking up, and then you're going to write. At the same time, I'm going to minus the MA to that side. Don't write this down yet. Look up. Here's what's going to happen. The MG just drops down like a domino. There's a minus MA where the minus T was, and there's a positive T there, right? Draw the arrows and write that down. Acacia, you might notice by plussing the tension and minusing the MA, they kind of just swapped places. I had a student a few years ago, she nicknamed this the Swappy Dance. And so I'll use that phrase. If I have a negative in front of what I want to get by itself, Swappy Dance. Put it to the other side. Now it's positive. Move the other side back here. Swappy Dance. Now I can plug in numbers. Now I'm going to put the T equals on this side because that's where we're used to seeing the thing by itself. What's M? The picture probably told me. Look at the picture. Find something. Yes, it's meant to be Captain Obvious. Don't overcomplicate it. G, 9.8, not negative 9.8. In fact, we decided to let down be positive because it made the math easier. You said it's going to be easier to let that be the winner, and it is. And then there's a minus 12. What's A? Mr. Dewick, the 4.2 is pointing down. Doesn't that need to be negative? No. We took care of all that with our winner minus loser shtick. We don't need to worry about whether it's negative or positive. There is you know what? There's the negative right there. What do you get? Did that one in your head, Mr. Dewick? Well, maybe. It's going to be 12 times what? 5.6? So 12 times 5 is 60. 12 times 0.6 would be 2.4 plus 2.4 plus 2.4. 67.2. I might be wrong. Is it? Okay. I can do math in my head. And units, newtons. It's a force. Okay. This is the usefulness. This is why I tried to tell you a good free body diagram and winner minus loser is the best tool I'm going to give you this whole unit. We're going to flog it to death. Example 8. Ooh. Find the tension in the rope if the mass is moving up at a constant speed. You know what? Constant speed is one of those trigger phrases that I would make a mental note of always. In fact, I'll usually just underline it in real life. Okay. Aiden, what's this question asking me to find? This is a job for a free body diagram. How do I know? There's more than one force here. So let's do a good free body diagram. Aiden, what are the forces acting on this 12 kilogram mass? Get the obvious one. Good. What else? Bigger, smaller, or the same size as mg? How the heck did you get same size? Okay, this is interesting. This morning, one of my students said, well, it's moving up, so tension must be bigger. Newton's laws tell us nothing about how things are moving. They only tell us which way things are accelerating. If we're at a constant speed, what's our acceleration? Which means forces must be balanced. Okay? Put your pencils down and look up. I'm going to do this wrong, but even if you do this wrong and you don't go work for Verizon, you'll be okay. I'll show you what my students did this morning. And I didn't dissuade them from it. They said, oh, up is winning, tension is bigger because we're moving up. I said, okay. And I did this. And then they said, who's winning? Oh, Dewick, it's easy. Tension, they said. Who's losing? Equals MA. Then I said to them, okay, get T by itself. How would you get T by itself here? Okay, they plussed the mg over. And then I said, okay, let's stick in numbers. Oh, yeah. They said, we can do this. And so they went, M is 12. A, as long as, and I'm going to be really negative, as long as you aren't dumb enough to say that meters per second is the same as meters per second squared, because you've had a physics teacher that has emphasized units with you, as long as you don't go work for Verizon and put a V in for an A, you'll notice something is weird. I don't see an acceleration anywhere. Now, by the way, if this is a multiple choice question, will I have one answer where kids put the 3.8 in for the A? Oh, heck yeah. Absolutely. Okay? So, this is where we got to, and I had a kid, oh, I don't see an acceleration, Mr. Oh, constant speed. What's the acceleration exactly as a number if you're at a constant speed? What's 12 times 0? In fact, Now you're going to pick up your pencil. I'm going to erase all of this. Aiden, this is what you said. You said it's a tie. It's balanced. Tension equals mg. You can go straight to writing that down because it's constant speed. Oh, what if it had been at rest? Same situation. Newton's laws don't tell us how things are moving. They tell us how things are accelerating. And if you're at rest, you're also acceleration of 0. That's going to be a challenge. In fact, I'm going to make a prediction. I'm going to get you all once or twice during this unit where you're going to start to look at an object's speed and think Newton's laws can tell you something about that. No, they don't. They tell you something about acceleration. Aiden, what's M? G? What do you get? I do this in my head. It's going to be 120 take away 2.4. 117.6, I think. Yeah. 4 sig figs in your head, Mr. Dewick. You are ever so clever. Thank you. I'm all blushing. Please, no more compliments. I'm all embarrassed. I like example 9. I like example 9. I like example 9. Jada, what's example 9 asking me to find? Do you see a VI or a VF or a D or a T anywhere in this question? So I'm not using those 4 equations from 2 units ago. Did they give you a force? Do you see a number with newtons next to it? This is a job for a free body diagram. So that was my reasoning. Find A. I don't see a VI or a VF. I'm not using that. Okay, probably a good free body diagram right here. What are the forces acting on this, Jada? Get the obvious one. Yes. What else? And your hint is, read the question. Mass is not a force. Start at the beginning and read the question. Suppose the... Keep reading. There's the Newton's tension. Like you're feeling right now, but a different kind of tension. Is tension bigger, smaller, or the same size as mg? You know what? I don't know. Because I don't know which way this is accelerating. Wait a minute. Get your calculator out. Calculate mg, 12 times 9.8. What do you get? Oh, you know what? I think you get 117.6, yes? How big is tension in newtons exactly? Jada? How big is mg exactly? Which one's bigger? Tension must be smaller. Oh, if tension had been bigger, like 160, I would have made that arrow bigger. By the way, looking at that free body diagram, which way are we accelerating then? Which way must we be accelerating? Which way do we have an unbalanced force? All down. Newton's laws tell us about acceleration. So now, which way are we accelerating? You said it. Which way is the winning direction? Same answer. Who's winning? Which force is winning from my free body diagram? Who's losing? Equals. What does it always equal? There you go. This is why I cannot teach you every equation. You're going to have to derive them yourselves, but it comes from winner minus loser equals MA. What are they asking me to find here, Jada? How would I get the A by itself? How will I move that M over? And I'm lazy. I'm fine if you all just go like this. You don't need to rewrite it if you don't want to. I'll know exactly what you were trying to get across. You wrote the original equation. Get the M by itself. Okay. In fact, I think now I can go to plugging in numbers. Jada, I'm going to put A equals because that's where we're used to seeing the A thing. M, how big? G, 9.8. Not negative. We took care of that in our winner minus loser shtick. Minus 98. All over 12. I would encourage all of you to try typing that into your calculator. We're going to get far more complicated fractions than this coming up, but it starts here. You've got to be able to handle this. And then we'll eventually have 4 or 5 terms on the top and 4 or 5 terms on the bottom. But we'll get there. Oh, I can make a prediction. Before you tell me the answer, there is a built-in error check. Anytime you have a hanging mass, if we cut the rope, what's the maximum the acceleration could be in free fall? 9.8. There's tension. You're going to get an answer less than 9.8 because the rope is slowing them down. So I have a bit of a built-in typo error check. If I get an answer bigger than 9.8 for a hanging mass, I've messed up. What'd you get? Jada, what'd you get? I think I'm doing some quick math in my head. You're going to get a little bit bigger than 1, I think. This is roughly 12 point something divided by 12, roughly. What'd you get? So did you put brackets? First of all, did you use your fraction button? So brackets around the top, 12 times 9.8, take away 98, close bracket, divided by 12. Okay, don't clear your calculator. Units, Jada, it's an acceleration. Meters per second squared, I hope is what you said, right? Right. Okay? So before you go to the next page, as far as I'm concerned, and this is what I said, I can give you any one of tension and acceleration, and you can find the other one. In fact, I'm going to go one step further. I could even ask you to get the G by itself. I could put you on a strange planet and say, hey, what is the acceleration due to gravity? You can get the G by itself. In fact, I could even ask you to get the M by itself. I could say, how big must the mass be? That one's a bit trickier because there's 2 M's, but we'll get there. Next page. Mr. Dewick, M equals 92 kilograms, jumps out of an airplane. Mention I jumped out of an airplane because I have. Once he pulls his parachute, air drag has a force of 1,250 newtons. Okay. I can do this. Maybe. Braden, what are they asking me to find? Do you see a VI? Or a VF? Or a D? Or a T? Do you see a force in newtons? This is a job for a free body diagram. Here's Mr. Dewick in free fall. What are the forces acting on Mr. Dewick? Get the obvious one. Yep. What else? The question gave me one. I used a phrase, so keep reading the once he pulls. What did I call that mystery force? Yes. Air drag or drag. How big? Is that bigger, smaller, or the same size as mg? I don't know. Wait a minute. Did they give me my mass? Quickly on your calculator, crunch mg. What do you get? What'd you get? It's just 92 times 9.8, right? What'd you get? Say it again. How big is air drag? Which is bigger, mg or air drag? Exaggerate it. And I'll call it F. You could call it F air or F drag or F air drag. I'll call it F drag. See how we put that all together? By the way, if you're really lazy and in a rush, to calculate mg, I'll often just go mass times 10 because that'll be really close to the 9.8. And then I can, it's obviously larger or obviously smaller unless they're really close numbers. Okay, Braden, what's my equation? Who's winning? Who's the loser? Equals? Yes. Again, for someone jumping out of a parachute, don't want to jump out of a parachute. Let's try that again. There's a Freudian slip, right? You say one thing, but you mean another. For someone jumping out of an airplane, as far as I'm concerned, I can either tell you the person's acceleration and say, find air drag, or In this case, I'm giving you air drag and saying, find the acceleration. How would I get the A by itself? Scott's theorem. Also, again here, built-in error check. If I had no parachute at all, what's the maximum I could be accelerating at? You're going to get an answer less than 9.8. Hopefully way less than 9.8, because I want to live. 1250 minus 92 times 9.8 all over 92. Again, practice typing that into your calculator, please. I get, Braden, did you get 3.79? Yep. Units, it's an acceleration. Good. Let's look at a little cliff jumping. Caleb jumps from a 19.5 meter high cliff into a lake. Assuming his mass is 65 kilograms. Ella, what's A want me to find? Time. You know what? Now let's go back to our kinematics methods. I'm going to go T equals question mark. I'll make my list. This is not a job for a free body diagram. What else do I know? Oh, when you're cliff jumping, I know the acceleration. And now we'll call it negative again, because in that unit we did let down be negative. What else do I know for cliff jumping? What's D? Negative 19.5, because it's actually not a distance, it's a displacement, and we ended up below from where we started. Oh, we said for cliff jumping we also know VI. We're going to assume it's 0. They might jump up a tiny bit, but it's not like they're taking a massive run and jumping down or jumping up. They're basically stepping off. So Ella, I'm looking for an equation that's got a T, an A, a D, and a VI. There is one. Oh, you waste. What? D equals VIT plus a half AT squared. Scratch the first part, though. So just pretend I said D equals a half AT squared. Okay, good. Because VI is 0, we can say D equals. In fact, I say a half AT squared, but I'm so lazy, I don't even write the I just write the half part, the 2. What are we getting by itself? Times the 2 over, divide the A over. I usually do that right on this line. And that gives me a T squared. A T what? A T squared. How to get rid of a squared. I remember this, Mr. Dewick. I will still ask you questions like this. Kinematics is still fair game. Why? Oh, because in kinematics we also found acceleration, so there's a fair bit of overlap. T is going to be the square root of 2 times D over A. It's going to be the square root of 2 times negative 19.5 all over negative 9.8. I'm doing some quick math in my head. This is almost exactly the square root of 4, so you're going to get really close to 2, I think. Like 1.98 or 2.01 or something like that. Or 1.99 or something like that. Let's see. Yeah, 1.9948. I'll write down 1.99, but I'll store this on my calculator. That's a fair bit of free fall. That's pretty much 2 seconds of free fall time. This is a pretty intense cliff jump. $19.5 meters is fairly high. Cohen, does that work okay? Yeah. Good, Cohen. What's B want me to find? Okay. I'm just going to go VF equals question mark. I'm not going to relist everything because I've got it in part A. How can I find VF, Cohen, my friend? And I have no problem if you do it that way. Cohen, have we been doing physics for a while? Say yes. I'm now going to say I'm willing to use an answer to find an answer if it's not a test and it's lazier. Is this a test? What's a lazier way to find VF using an answer that we already found? Help me out, folks. What's a lazier way to find VF? I would use VF equals AT on my homework now. I totally would. I would go, you know what? It equals VI, but that's 0. It equals AT. And Braden, because that allows me to use my answer button for the time, I would write negative 9.8 times 1.99, but I would go negative 9.8 times answer button. Hitting the water at negative 19.5 meters per second. Okay. Fahim, what's C want me to find? Is this a job for a free body diagram? Convince me. What else did the question give you? In? Give me a distance. I don't think this is a free body diagram. I don't think I'm going to find forces using winner minus loser equals MA. I think because they gave me a distance, or if I'd seen a time or a VI or a VF, I'd lean there first. So I'm going to say A equals question mark. And then let's list my data. What's that 2.5? Should I make that negative or positive? The answer is it's really up to you. Okay? You said negative, so I'm going to do that. So what you just decided, Fahim, is that down is negative. When this person is in the water, which way are they moving? Be obvious. Down. Are they speeding up or slowing down when they're in the water? Which way are they accelerating then? Up. You let up be positive, we're going to get a positive acceleration. Okay? If you had decided to let the 2.5 be positive, you would let that way be positive, then you're moving this way but you're slowing down. How did slowing down show up in an acceleration? Negative. You would get a negative acceleration, same magnitude, but you would have a negative. I would give you full credit for yours because you just decided I'm going to let down be positive. Einstein was right. It is all relative. There is no correct way to let positive and negative. It's whatever you want that makes your life easy. But since Fahim said down is negative, okay. What else do we know? Fahim, I know VF. I disagree. Can you read to me the first phrase starting with the word if and ending with the word lake? What am I trying to suggest if his feet barely touch the bottom of the lake? What's his VF? That's what I was trying to hint at, okay? Well, did they tell me VI when he hits the water? What? Ah! Negative 19.5. Gotcha. In fact, I'm going to use my answer button there. Okay. Which equation, Fahim? Get the A by itself. Yeah, VF squared equals VI squared plus 2AD. You used to be good at this. Get the A by itself. I'll give you a hint. The VF squared is what drops down like a domino. I know it's been a while. Then what? Okay, there is going to be a divided by 2a. But we always did our division last, so I'm going to say, what else? Minus the vi squared. And then all of that divided by the 2a? The 2a? Ah. Good. Okay. 0 squared minus negative 19.5 squared. I'm going to hit my answer button right there, squared. All over 2 times negative 2.5. Because you let down be negative and we've reasoned that we're accelerating up, we better get a positive answer with your reference frame. Is this a fraction? Brackets around the top. Oh, also brackets around the bottom. I got 76.44. Yes? No? Am I right? Yeah? Did you use the answer button on your calculator, or did you use negative 19.5? So you typed more work for less accuracy rather than just using your answer button. Oh, I thought I taught you better. It's okay. By the way, I would give you full credit for that. But whenever possible, I'll use my answer button, right? And it worked out with no decimals, or sorry, with no repeating decimals, which was nice. Is it 76.44? Anybody else? Yeah? Okay. How many G's is that? It's around 8, which is high enough you would not want to blow the landing, the entry into the water here. You certainly would not want to belly flop this, but even if you accidentally landed a little bit sideways, you could, for example, dislocate your shoulder or something like that. You would want to make sure, if you were doing this, that you were very tucked and streamlined. Next page. Maddie, did that work okay, or are you still redoing it? Worked? Okay. Next page. That's my way of saying turn the page. Or next page over. What's D asking me to find, Maddie? Can you read to me the question? And I'm going to interrupt you and ask you to repeat something, not to make fun of you, but to make a point. So read the question. The what force? The what force? The what force? The what force? If you ever see that trigger phrase, the net force, if you ever see this, well, first of all, F net equals what? From your formula sheet. This is saying skip the free body diagram. You've already done it in your calculations without realizing it. No F, B, D required. You can go straight to F equals what? MA. What was M? What was M? 92. Thank you. What was A? 76.44, or answer button. 65, not 92. Is that right? Well, then who said 90? Boy, won't listen to that person again. 65. Okay, that's better. So 65 times answer button. I get 4,970. Is that what you got too, Ella? 4,970 newtons. Is that a lot? Well, you don't know yet, so I'll put this into perspective for you. A Major League Baseball player swinging a baseball bat gets about 7,500 newtons. So this is about 2/3 of getting hit by a Major League Baseball player's bat. Would you want to hit this water at an angle awkwardly? No, you would not. You would want to take this on the soles of your feet and be very, very, very streamlined.
Absolutely. It was so nice to see you, but I'll see you on Tuesday. Have a
wonderful Easter.
Yeah.
Take care, Hunter. Okay. So 5,000 newtons is, you don't want to be hit by that. 100 newtons, meh. 500 newtons, oh, a little owie, but depending on where you hit me, I can shrug it off. 5,000 newtons, I'm ducking. Example 12. What does FBD stand for? Oh, okay. Draw a free body diagram for a cyclist moving to the right at... I would underline that mentally while pedaling. Okay. Ella, we can do this, you and I. What are the forces acting on this cyclist? Get the obvious one. Okay. Also, because if I force you to get the obvious one, you've written something down, you feel better, you're more relaxed, right? That's a G, by the way. Is this cyclist sinking into the ground like quicksand? Are they flying into the air like Superman? So vertically, the forces are balanced, so there has to be an arrow pointing up the same size. What's exerting the force up? Ground. Yeah. Be obvious. Again, it's weird to think that an inanimate object is exerting a force, but it has to be. Newton's law says it has to be. Otherwise, you would be sinking into the ground like quicksand. Okay. I'd like you all to imagine that you're cycling, and you're cycling at almost your fastest speed. Okay? What do you feel? What forces do you feel acting on you? Which way? Let's pretend you're cycling. Oh, to the right. So it seems to me, Ella, I would say that there is air resistance. Why can't that be the finished free body diagram? Why is that impossible for this specific situation? How big must there be an arrow pointing in the other direction? Same size. What's that? It's complicated. I'm going to say F pedal. That's not right, because riding a bike is actually way more complicated than you realize. Your legs are moving up and down vertically. They're applying a vertical force to a rotor, which then changes that to a linear force, which sends it to a hub on the back, which then sends it to a tire. If you actually want to know what's pushing you forwards, I can tell you. Can you ride a bike easily on ice? Friction is actually what should be. I should have said force of friction, but I'm just going to say it's how hard you pedal for now. Okay. What if you're pedaling as fast as you can, but you still want to accelerate? What other force can you control here? Yeah. How? We've just explained the Tour de France. Right? The pose that they all adapt, every one of them has spent hours in a wind tunnel, and some physicist or engineer has said, okay, you need to drop your left shoulder 1 centimeter. Good, good, good. Okay, you need to drop your hips about 2 centimeters. Good, good. Okay, you need to raise your head about a half a centimeter. Memorize that. That's your body's most aerodynamic pose for you. And they've memorized it. Because everyone's going to be slightly different depending on their body shape and body type. But yeah, you want to speed up? Tuck. Is that okay? So I always like it when we get some Captain Obvious physics that explains something that we've seen all the time, and oh, now I know why. Example 13. Draw a free body diagram for an inline skater who's dragging the toe of one skate in order to slow down and stop. Let's pretend, like the biker, that the skater is also moving to the right. This is a job for a free body diagram, because they said to draw a free body diagram. Okay. Can do this. Claudia, I know you're away, but you can handle this. What are the forces acting on this person? Get the obvious one. What do I mean when I say get the obvious one? Gravity. I said yesterday, I'm always going to teach you to go systematically. For a complicated question, by the way, you're going to be so tempted to try and go to the force that they want you to find right away. Don't. Save it for last. It'll become obvious. Gravity. Is this skater sinking into the ground like quicksand? Are they flying here like Superman? That means vertically the forces must be, I'm looking for a word that starts with letter B. Good. And we'll call that F ground. By the way, we're going to give that force a special name in a few days, but for now, we'll just call it F ground. If you said F pavement, I'd be fine with that, or F sidewalk, I'd be fine. Okay. Which way is this person moving? I said to the, starts with letter R. Right. Are they speeding up or slowing down? Okay, they're moving to the right, but they're slowing down. Which way are they accelerating? Which way are they accelerating? Left. Which way must there be an unbalanced force pointing? Same answer. Left. Has to be a force pointing that way. Has to be. Otherwise, it would be impossible to be decelerating and come to a stop. What force is that? I heard someone, I think, say it. Did I? No, I thought I did. Okay. What force is that? Dragging, and I'm going to call it friction this time because I want to use the proper name. So I'm going to say F. What else? Friction, F-R-I-C. What else? Is there anything else? Let's see. That picture there, is that enough for somebody to slow down and come to a stop? They're moving to the right. Doesn't that mean there has to be a force pointing to the right? No. Newton's laws, Cohen, tell us nothing about how things move. They only tell us about how things accelerate. Which way will that picture accelerate? To the, I'm looking for a word that starts with the letter L. Left. If you're moving to the right but you're slowing down, which way are you accelerating? To the. That's all you need. That is the free body diagram of a skater dragging their foot. This question and the next question are the ones that I mentioned. I was at a physics conference and I had a physics teacher get these wrong because they had, don't write this down, they had F push. Oh, they're pushing with their foot. No. You don't need that. Don't need that at all. Example 14 says, draw a free body diagram for a car hitting the brakes. Okay. I can do that. What are the forces acting on it? Get the obvious one. Everybody. Good. Is the car sinking into the ground like quicksand? Is it flying here like Superman? So I know the ground is pushing up. Let's pretend the car is driving to the right and it's slowing down. If it's driving to the right but it's slowing down, which way is it accelerating? Which way must there be an unbalanced force? Oh, and it's friction. You know how I know it's friction? Because cars can't stop on ice. If you're ever wondering if something is friction, just ask yourself, does it work on ice? No, friction. Guarantee. At the physics conference, don't write this down. Another teacher had this. No, your engine is not what makes a car go forwards. And the way I know that is if you put a car on ice and rev the engine up, it doesn't go anywhere. That's the free body diagram right there. Just that. Okay. What's your homework? I'm going to be giving you a bunch, but you're going to have some time to work on this on Tuesday when we get back. So you can circle question number 1. If you look at number 1, this is the hanging mass tension question that we did a couple of examples of. So a rock is attached to a rope is attached to a 2 kilogram rock. M is 2 kilograms. And then in part 1, it says draw a free body diagram and find tension when you're accelerating up at 6 meters per second squared. You'll probably need to do this on a separate piece of paper. In part 2, accelerating down at 1.5 meters per second squared. Accelerating down, accelerating up, accelerating down, or 0. See if you can solve those. Circle question number 2. In question number 2, I'm giving you the tension and saying, find the acceleration. It's a mini curveball because I haven't quite done one exactly blatantly like that. I'm curious to see if you can have the aha moment. You can skip number 3. Oh, there is no number 3? Funny, Duick. 4 and 5 is good. But you can skip number 6. 7 is good. You can skip number 8. 9 is a question that is so easy that it's tough. It's a tough question. Circle it, put a star next to it. That's my way of saying, ask me about it after you've tried it if you can't get it. But I want to see again if you can have the aha moment for part A, B, C, and D. 10 is good. 11 is good. 11 is a bit weird. On my copy, I always get this weird graphic distortion. You folks have 4 nice free body diagrams to look at for number 11, don't you, I think? I don't know why mine does a big situation. It does that every year. I don't know why, but it photocopied on yours. Okay, yeah? Okay, so number 11 is good. 12 is good. 13 and 14. Put your pencils down, look up. We watched part 1 of a video yesterday, part 2 today.
If I apply a force to the globe, I can actually get it spinning in roughly the same way that the Earth spins. But it is tricky. There's very little friction on the bottom because of it being supported on this thin layer of water. And you can see the more force I apply to it, the more it accelerates. Ooh, so we're getting it speeding up here.
When you push that, like, it's not too easy to get it going. Why is that?
Friction, probably.
So strange.
Why is it not really easy to push? What is it about this giant sphere that makes it a challenge to push?
The weight. The resistance.
What's weight a measure of? The force of gravity. That's not what's making it difficult to push. What is making this thing difficult to push? I'm looking for a word that starts with letter I. Inertia. That's that thing that objects with a lot of mass possess that makes it difficult to change their motion state. I pick my words very carefully. It's what makes stuff tough to push, but there's some flaws in that definition. This thing is so massive, it has so much inertia. To get it moving, you got to put a force into it. But once you let it go, it'll keep moving. To get it stopped, you also got to apply a big force.
Gravity.
It's really heavy, too, so I'm pretty sure the weight of it sitting down is making it tough, too.
You don't think its weight is supported by that water?
Well, I know it's supported, but...
In fact, in the free body diagram, gravity down, water pressure up, I think they're balanced. I think the net force on this is 0 until people start pushing on it from the side.
Even though it's supported down, moving it, it's still, like if the center of gravity is here, we still have to push the weight coming out from here. So it's pretty heavy, I'm pretty sure. Most people will say if you just apply a force to it, it starts moving. That's not really the point I want to make. The point I want to make is the more force you apply to it, the more it speeds up.
What's the fancy word for speeds up? What Derek is really saying is, I want you to realize F equals what? MA.
The more it gets going faster and faster and faster. But it's got 2.5 tons of inertia, so you can really feel that you have to push hard to accelerate it.
What do you feel when you push on it?
Just moves.
When you push something, it moves.
Does it do something more than move?
When you apply a force on it, what's a better word than move? Starts with letter A. It's accelerate. This is why I'm saying Newton's laws tell us nothing about motion, Cohen. They tell us about acceleration. Right? Right.
Spinning.
It's
rotation. Velocity. Speed. There's some word you're looking for.
There is a word I'm looking for. What do you feel? Is that hard?
Not really.
It's easy?
It's not going very fast, though.
It's not like hard to push, but it's sort of hard to get going fast.
It's too big to make it fast.
Is it hard to make it fast? Why is it hard to make it fast? Can we try?
Yeah.
Let's try it. Let's get it going really fast. Ah. How is that?
Rotating.
Oh,
Spinning.
so close.
Moving.
How do you make it go faster?
You only need to push hard, and more harder than that.
How do you make it go faster? Push hard. Apply a force. This kid's getting it. Okay? Didn't use the physics terms, but this kid's getting it.
You put a force on an object, a net force, an unbalanced force, and it...
And it what? Accelerates. But you can see, this is not an intuitive concept. Newton's laws are not easy to wrap your brains around. Don't kid yourselves. If you're finding this tough, you're normal.
Come on.
Goes.
The least scientific whatever. It goes. You study physics, right?
Yeah.
So that kid is taking physics, and he's struggling with this. I'm telling you, this is tough to wrap your brain around.
Which means I'm probably looking a little bit like a moron here.
No, you're
but
not
that's
looking
okay.
at all.
It's easy to push, but like if you try to go fast, then it just sort of stays the same speed.
Did you hear what he said? It just sort of stays the same. He's starting to pick out Newton's first. When you stop pushing on it, it keeps going because there's no forces acting on it. Not bad.
But could you bring it to a stop?
Probably not. Definitely not.
Can you give it a shot?
It's stop the water. Well, other than cheating, yeah.
What do you think?
Not gonna happen.
Come on. Get back into it. You can do it.
I don't think it's gonna work. You can give it a shot. Kinda.
What do you see there?
It's stopped, but it's only stopped because it's on like a very soft thing of water. Pretty much, I'm pretty sure.
So they've stopped it, and he's saying, but the only reason it stopped is because there's a force acting on it from the water. Is that correct? No. In fact, if it's at rest, the forces must be, I'm looking for a word that starts with the letter B, means there's no net force acting on it. Which means if they walk away, it shouldn't spontaneously start spinning.
So it's not going to stay stopped or what?
It shouldn't. Huh. Alright.
Are you applying a force to this sphere here?
Yes.
What happens when you apply a force to the sphere?
Then it changes like speed.
What's a fancy physics word for changes speed? There it is. This kid just got Newton's second law and Newton's first. An unbalanced force changes speed. Good.
That's a pretty awesome observation you just made.
Yeah.
Do you know that?
I guess.
So we could generalize. We could say force causes
change.
And?
Speed.
Man, you were nailing it. Can you give me a high five? Boom. What do you think physics is?
Like how things work, I guess.
And you want to know how things work?
Yeah.
How old are you?
11.
You seem pretty smart for being 11.
Okay.
Do people tell you that you're smart? Do
No.
you think you're smart?
No.
I think you're smart.
Okay.
You take my word for it?
Okay.
Really?
Yeah, I guess.
Newton's laws are not intuitive. You saw the people that struggled the most, teenagers and adults, who had some physics background. And again, I've been to conferences, and again, I've been fooled many, many times by these thought puzzles, by other demonstrations that I'll show you. So if you're finding this tough, you're normal. There's 7 minutes left. Try number 1, or try finishing off the homework from last day. Otherwise, don't be staring at your phones. Yeah, I said it. Have a good Easter weekend when the tone goes.